When we looked at binary search, we talked about how efficient it was. So let's just spend a little bit of time informally understanding how we look at efficiency of algorithms. So in general, an algorithm will work on many different sizes of inputs. So it makes sense to talk about the efficiency as a function of the input size. So if the input size is n, we will use a function such as t of n to talk about the time taken on an input of size n. Now, of course, different inputs will take, even of the same size, different inputs will take different time for an algorithm to execute. So which of these should we take as our measure of efficiency? The convention is to use the worst case behavior. So among all the inputs of size n, which one will force our algorithm to take the longest time? And this is what we call usually the worst case efficiency. Now, in the case of searching, for instance, binary search or even a linear scan, we said that the worst case would occur typically when the value that we are trying to find is not found in the sequence. So we actually have to scan through the entire sequence or array or list before we find it in case of a linear scan. And in terms of a binary search, we have to reduce the search interval to a trivial interval before we can declare that the value is not there. So that's the worst case. Now it may turn out that in many algorithms, the worst case is rare. Right? So it may not be a representative idea about how bad or good the algorithm is, and maybe it would be better to give something like the average case behavior. Now, unfortunately, in order to determine something like an average case in a mathematically precise way is not very easy. We have to have a probability distribution over all inputs and then measure different inputs and different outputs and then compute a probabilistic mean for this. So in most cases, this is not possible, which is why we settle for the worst case efficiency. Now, when we talk about efficiency, as we said, we are broadly interested in the connection between input size and output size. So we express this up to proportionality. So we are not really interested in exact constants. We want to know, for instance, is t of n proportional to log of n, for example, in the case of binary search, or n in the case of linear scan, or larger values like n log n squared, n cubed, or is it even exponentially dependent on the input? Is it 2 to the n? So we write this using this what is called the big O notation. So if we say t of n is big O of n, what we mean is that t of n is some constant times n. Same way t of n is big O n log n means t of n is some constant times n log n. In other words, it's proportional by some constant to that value. So we are not going to go into much detail in this course about how big O is defined and calculated, but it's useful shorthand to describe the efficiency of algorithms. So we will use it informally, and you can go and read an algorithms textbook to find out how it is more formally defined. So in terms of this notation, when we say that linear scan is proportional to the length of an array or a list, we can say that linear scan takes time big O of n. In the same way, for a sorted array, binary search will take time big O log of n. So here is a table which tabulates for different values of input n, what would be the corresponding values of log n, n log n squared, and so on. And what we want to probably estimate is, given these values, these absolute numbers, what would be reasonable inputs that we can expect to compute within a few seconds. Now, if we type something on our computer and we don't get a response very soon, these days, we realize that something may be wrong. So let us say that we want to see the input in 1 or 2 seconds, otherwise we will deem it to be inefficient. So if we look at this, we have to now figure out how fast our computers are. So by some simple hand experiments, you can validate that Python can do about 10 to the 7 basic steps in a second. So what we can do is try and execute a large loop and see how much time it takes. So here we have a bunch of programs which we've already written, and here is a template. So if I say look at speed 4.5pi, it basically executes a loop 10 to the 4 times, hence the name 4. So for m in range 0 to 10,000 minus 1, it just assigns m to be the value I, and finally there's a statement we haven't seen so far, but which should be quite intuitive. It says print the value of m. So in the same way, speed 5 does this for 10 to the 5 times, speed 6 does this 10 to the 6 times, speed 7 does this 10 to the 7 times, and so on. So these are a bunch of scripts we have written for Python from speed 4 to speed 9. Now, if you are working in Unix or in Linux, there is a nice command called time. So first of all, I can take Python and I can directly use the name of the Python program like this. So I can say Python 3.5 and give the name of the script and it will execute it and give me the answer. But now, in addition, there is also a useful command called time. So time tells us how much time this thing takes to execute. And it typically reports this in three quantities: real time, user time, and system time. So what we really need to look at is the so-called user time. Okay? So it says that if I do this loop 10 to the 4 times, it takes a fraction of a second, 0.03 seconds. If I do this, on the other hand, 5 times, then it goes from 0.03 to 0.5. So it's roughly a factor of 10, as you would imagine, which is reasonable. Okay? And if I do this 0.6 times, then again it goes up, not quite by a factor of 10, but it's gone up to about 0.2 seconds almost. Okay? Now we come to the limit that we claim, 10 to the 7. So if we run speed 7.py, which is a loop 10 to the 7, it takes about 1 second. I mean, this is not a precise calculation, but if you run it repeatedly, you say that each time, because there are some other factors like how long it takes for the system to load the Python interpreter and all that. But if you just do it repeatedly, you see that 10 to the 7 takes about a second or more. So this is the basis for my saying that Python can do about 10 to the 7 operations in a second. And just to illustrate, if you actually do it for 10 to the 8, you can see it takes a very long time. And in fact, it takes roughly 10 to 12 seconds to execute. So soon we will hopefully see the output. So as you can see, 10 seconds doesn't seem to us like a very long time, but it is an enormously long time when you're sitting in front of a screen waiting for a response. So what we claim now is that something that takes a couple of seconds is what we will deem as an effective input that we can solve on our computer. So coming back to our table, assuming that 10 to the 7 is the limit that we are looking at, let us see what happens when we mark off 10 to the 7 on these different columns. So it turns out that if something takes log n of time, then even for 10 to the 10, it takes only 33 steps and we are fine. Of course, if the input is linear and we're ignoring the constant, then an input of size 10 to the 7 will take time to. So this line comes here. On the other hand, if we have n log n, now it turns out that n log n, so it's useful to know that 2 to the 10, as we mentioned before, is 10,000, is 1024, right? So therefore, 2 to the 20 will be 10 to the power 6, okay? And 2 to the 30 will be 10 to the power 9. So really, the log grows linearly as this thing grows in terms of powers of 10. So when we have 10 to the 7, the log is going to be something like 20 something. So it's going to be of the order of 10. So it's going to drop 1 0. So that's why we say that for input of size 10 to the 6, okay, the log is going to contribute a factor of 10. So that's going to take time 10 to the 7. Now notice that when you do square, then 10 to the 3 is already going to take 10 to the 6. So somewhere between 1000 and 10,000, say around 5,000 maybe, if you're lucky, will be the feasible limit for something which takes n square time. And as we go to n cubed, the limit drops from a few thousand to a few hundred. So here we have between 10 to the 6 and 10 to the 9. So somewhere between 100 and 1000, the scaling goes from 10 to the 6 to 10 to the 9. So where 10 to the 7 will be somewhere around 200 or 300. And when you get to the exponentials, like 2 to the n and n factorial, then unless you have an input that is really small, like 10 or something like that, you're going to hit problems. Because if you have a few tens, you already get to enormous numbers like 10 to the 30. So this gives us an idea that given that our system that we are working with, Python, can do about 10 to 7 steps in a second, we need to really examine this table to understand what kind of inputs will be realistic to process given the type of algorithm that we are executing. Now, Python is 10 to the 7. Python is a bit slower than other languages, but even if you're using a very fast language like C or C++, you cannot really realistically expect to go beyond 10 to the 8 or 10 to the 9. So this table is more or less valid up to a scaling of a few tens, okay, in different languages. So you can take this as a reasonable estimate across languages. So theoretically, if you look at algorithms books or complexity theoretic books, any polynomial, any dependence on n which is of the form n to the k for a constant k is considered efficient. So these are the so-called polynomial time algorithms. So n cubed, n to the 5, n to the 7, all of these are considered to be theoretically efficient algorithms as compared to 2 to the n and so on. Right? So you have n to the 7 versus 2 to the n. So n to the 7 is considered efficient, 2 to the n is not. But what the table tells us, if you look at the previous table, is that even n square has a very severe limit, right? We can only do about 4 to 5,000 things. So if we are doing something in n squared time, we can't process something larger than a few thousand. Now, many of the things that we see in real life, like if we have a large spreadsheet or if we have anything like that and we want to sort it, then it's very likely to have a few thousand entries, right? So supposing even if you want to just look at all the employees in a medium-sized company or all those children in a class in a school or something like that, a few thousands is not at all a large number. So therefore, what we see is that if you go beyond that, an n-squared algorithm would take enormously long time to compute. So really we have to think very hard about what are the limits of what we can hope to do. And that's why it's very important to use the best possible algorithm, because by using something which is better, you can dramatically improve the range of inputs on which your algorithm works.